Now we define the gradient vector. What is gradient vector? From the definition of directional derivative, we have duf, that is fx at xy times a plus fy xy times b in the 2 dimension, and in 3 dimension as this vector, that is fx at xyz times a plus fy xyz times b plus fz xyz times c. That's the directional derivative. But from the definition of directional derivative, we see that duf can be written as the dot product of 2 vectors. Like in 2 dimension. In 2 dimension, we see that duf, that is fx xy fy xy, this vector dot product a b, that actually is fx at xy fy xy dot u, and in 3 dimension, yes, in 3 dimension, that is fx xy z fy xyz fz xyz dot u in 3D. Now we see that the directional derivative can be written as the dot product of 2 vectors. We give the first vector or name we called the gradient of f. Gradient f. Sometimes we write as nabla f. This symbol called nabla f, that is fx xy and fy xy. We call this vector the gradient of f in 2D. In 3D, it write as fx xyz fy xyz and fz xyz. That's the definition of gradient vector. These 2 are 2 notations for the same vector. That's actually all the partial derivative. All partial derivative determine a vector. This vector called gradient vector. Let's see an example. If fxy equals 1 over x squared plus y squared, find gradient f. The gradient f, that is fx fy, because this is 2 dimension. The fx as partial f partial x. Use the quotient rule as 1 over, or use the power rule. Use the power rule, that is x squared plus y squared, that's our power -1. We take the derivative for x, that is negative x squared plus y squared -2, then times the derivative in bracket, that is 2x. So that is 2x negative 2x over x squared plus y squared. And take the square. And this for fx for f and y are that is symmetry for x and y. So partial f partial y, that is negative 2y over x squared plus y squared and square. So the gradient f, that is negative 2x over x squared plus y squared square, and negative 2y over x squared plus y squared, and then the whole square. That's the gradient. And from the definition of directional derivative, we know that the directional derivative of f can be read as gradient of f dot u, that is actually the length of gradient f times the length of u times cosine theta, because u is a unit vector, so that is actually gradient f times cosine theta. So the maximum is cosine theta. Cosine theta equals 1 as the maximum. The maximum of duf. That is the direction of gradient is the maximum of the directional derivative. So the direction of gradient is the maximum of duf. Then the direction of derivative is the maximum of duf, and the unit vector in the gradient in the direction of gradient is the maximum if u then duf equals gradient f times the gradient f cosine theta. Cosine theta is 1, so that is gradient f, so maximum duf. So that is the value of maximum for duf. That is the length of gradient. The length of gradient is the maximum, and u equals negative gradient f over then duf equals negative the length of gradient f, that is minimums. So the maximum of directional derivative is the direction of gradient, and the minimum of duf is the negative direction of the gradient from the direction derivative, the definition of directional derivative. Now let's see some examples. If fxy equals 1/2 x squared plus y squared and p naught is 1, 1, find the first example. The first problem is find the direction in which fxy increases fastest at p naught, and the direction in which fxy decreases fastest as p naught. From the statement we state here in the second term, we know that the direction of gradient is the maximum, actually increasing fastest, and the direction of negative gradient is decreasing fastest. So first we find the gradient. Sometimes we write as gradient f as nabla f, that is fx at 1, 1 and fy at 1, 1. That is the fx that is x, fy is y, so at this point it's 1, 1, and the direction gradient f over the length of gradient, that is 1 over square root 2, 1 over square root 2. And this direction is the direction fxy increasing fastest. And the negative, that's the first problem. The second problem, that is the direction negative gradient f over the length of gradient f, that is negative 1 over square root 2, negative 1 over square root 2 is the direction where is the direction that fxy decreases fastest. That's the meaning of the gradient of f. For 3 dimension, if f x y z equals x cubed minus x y square minus z, the p naught is 0 or 1 1 0. Find the direction. In which f x y z increases fastest at p naught. And the reach. And find the direction in which increase fastest and the rate of change. The rate of change, that is actually the direction derivative. The direction derivative from the statement in the term 2, we have the direction, the rate of change in the direction in the gradient direction is the length of gradient. So first we need to find the gradient. The gradient is fx. Fx is 3x squared minus y squared. Fy, that is negative 2xy, and fz equals negative 1. So the direction, the increasing fastest, the direction gradient f over the length of gradient f. The gradient f at 1 1 0, that is x equals 1, y equals 1, z equals 0, and negative 2, negative 1. That is the length of gradient, that is square root line, that is 3. So that is 2 over 3, negative 2 over 3, and negative 1 over 3. The direction, this direction is the direction that fxyz increases fastest at p naught. This direction, and this direction, the rate of change is just the length of, and just the length of gradient. Is the length of gradient. In in this direction, the rate of change we just compute before that the length of gradient is 3. Okay, that's the definition and some related material for gradient.